So today we're going to be looking at implicit differentiation. So in a mathematical setting, a function or relation is defined explicitly if y has been completely isolated. So this would be an example where y is completely isolated from x on either side of the equation. Sometimes, however, it's not possible to isolate y and convert it to an explicit form. So we have this example here, x squared minus y squared plus x plus y or times y equals 5. Implicit, we cannot isolate them. So we have some examples here, things that we're used to, differentiating x to the power of 8 with respect to x, giving us the answer of 8 of x to the power of 7. Another familiar example would be differentiating negative 2x to the power of negative 3 over 2 with respect to x, with the answer of 3x to the power of negative 5 over 2. Now when we get to y to the power of 4, we're differentiating this with respect to x still, and we don't know how to solve this. So it's not explicit, and we're going to use the chain rule to solve it. So we've got dy over dx equals dy times du over du times dx, or over dx, which is the chain rule. It's something that we're familiar with. And instead of using u, in this case, we're going to use y. So when we're doing this, we're still going to write it as y to the power of 4 in terms of x over dy times dy over dx. So we have 4y cubed times this tag along dy over dx. We differentiate the exact same way as we normally would, pulling the 4 down in front, subtracting 1 from the exponent, and multiplying by dy over dx from here. So it's important to note that these derivatives will always end in a tag along dy over dx. So we're just going to do a few examples now. So pause the video, try this one for yourselves, and see what you get. So we end up with negative 10 y to the power of 4 times dy over dx. Again, pulling the 5 down in front, multiplying by negative 2, and subtracting 1 from our exponent, and leaving the tag along dy over dx. So we have 4 more examples to do with this. So if you want to pause and try one or try all of them, take your time, and I'll go through each one. So this first one, we have 9x squared minus 4y squared, which we end up with 18x minus 8y times dy over dx. Again, nothing really changes with the x because we're multiplying, or we're taking the derivative in terms of x, but this is the one where it changes. This one, again, we're taking the derivative of 6y to the power of negative 1/3. So again, multiplying by negative 1 over 3, and then having negative 2 in front to the power of negative 4 over 3, with our tag along dy over dx. So our next one, we're going to use the product rule, since these two terms are being multiplied together. So we take the derivative of our first term, which is 4x to the power of 3, times our second term, y cubed, plus x to the power of 4, which is our first term, left, times the derivative of our second term, which is 3y squared times dy over dx. And then we're just going to do a little bit of simplifying, which really we're just moving this 3 to the front. So this would be our answer. It's not pretty, it doesn't look done, but it is. This next one, we're going to have to do the quotient rule since we have one over the other. So we'll take the derivative of our first term, 2x to the power of 5, leave our second term, subtract, leaving our first term, and taking the derivative of our second term, which is 6y with our tag along dy over dx. And then, as always, we leave the bottom term and square it, And even though it's in y, we don't have a tag along for this y. And this is our derivative. So again, multiplying 3 times 10 to get 30, 2 by 6 to get 12, with our tag along there, and then squaring the bottom, which is 9y to the power of 4. So again, not the prettiest solution, but it is done. So the true advantage of this type of differentiation lies in the simplification of functions before differentiation. So we're going to do this example next, where we have this function 2x over y plus y equals 7. So we're going to simplify it first. And we're going to multiply every term by y. So we have 2x plus y squared equals 7y. And we're going to take the derivative. So we have 2 plus 2y times dy over dx equals 7 times dy over dx, since we took the derivative of 7y, leaving us with just 7 dy over dx. The next part is we have to isolate. So we have to get these dy over dx is on the same side. So what I'm going to do is I'm going to subtract 2y dy over dx and move it to the other side. So I end up with this, and then I'm going to take out my GCF, which is dy over dx, leaving me with 7 minus 2y. Then I can divide both sides by 7 minus 2y. My dy over dx is completely isolated, and I have 2 over 7 minus 2y as my answer. The last example that we're going to do is again another simplification one. We have x cubed plus 6y to the power of 1 over 2 equals 25. And again, we can simplify this by squaring both sides this time. So I want you guys to take a minute and try this one on your own. So now that you've hopefully done that, you simplified it to be x cubed plus 6y equals 625. We're going to take the derivative, which is 3x squared plus 6 times dy over dx. And since 625 is a constant, the derivative of that is 0. And again, we're going to isolate 6 dy over dx. So we're going to move this 3x squared to the other side, making it negative, and then divide both sides by 6, which once simplified, we end up with negative x squared over 2. And so this is the first half of your lesson. So move on to the second set of notes once you kind of have a handle on these ones.